Um, Hello, everyone. Thank you for joining me to talk about working with NULL. Before I start, I do want to thank William Durkin and Ben Weissman for running this entire event, and James Phillips, who helped me get ready for today as my mentor. So first, a little about me. My name is Tom Freedman. I've been working with SQL Server since the year 2000 and since SQL Server version 2000 and pretty much every version since then. I got my MCSE in 2017 for SQL Server 2014-2016 before they retired that certification. I work for Trinity Life Sciences. We're a pharmaceutical commercialization consultancy. I work as a data warehouse development director. And in my free time, I like to attend indie rock concerts and to travel. So what I'd like you to take away from this session is a little more knowledge about where NULL comes from, what it is exactly, how it complicates things when you're working with it, some things to watch out for, and some strategies to make your own code better. So what is NULL and why is it so weird? I'd like to start with a great quote I found while researching for this presentation from Keith Hare, the convener of the SQL ISO Standards Committee. And he said, "The great thing about nulls is that you can spend hours talking about the meaning of nothing." And he was referring to the hours of debates that they had on the Standards Committee about how to represent null in the SQL standard and how it should behave in implementations. And there's a huge source of debate. I found this quote, speaking of debate, in a 150 plus post thread on an article on SQL Server Central from 2005. And those comments spanned 10 years. So a little history. NULL was introduced in the 70s by E.F. Codd when he was developing the relational model. He needed a way to represent missing information in the model. And since the beginning, NULL was one of the most controversial aspects. A lot of people argue that NULL shouldn't exist in the model, that the relational model should represent a version of the truth, and unknowns are not necessarily true, and so they don't belong in the model. And so a lot of people advocated, CJ Date among them, for a version of the relational model that does not include NULL. But E.F. Codd advocated for NULL, and later on advocated for two different nulls, null but applicable and null but not applicable. Another suggestion that Keith Hare mentioned came up during their discussions around the standards was having 128 user configurable nulls, so that for your problem domain, you could specify all the different reasons why you might be missing information in your database. Obviously, they felt that that couldn't be implemented or wouldn't be implemented by the people who are producing database software, and so they settled on having a single null. The reason why it complicates things and makes things weird is that it introduces three-value logic. Two-value logic is what most programmers would consider normal. It's things are true or things are false. If I say, is this value greater than or less than another value, that either returns true, it is, or false, it isn't. When you add unknown as an additional potential result, it makes things way more complicated. Another thing that makes things complicated to work with is that the SQL implementation, the SQL definition of null, is inconsistent deliberately depending on the situation in which the null is being used and worked with. So that can lead to a lot of confusion for developers as they're learning and working with SQL. So what is null really? Null, as I said, denotes missing information. It's not a value, it is a marker on a field, and it indicates the value is unknown or it's not applicable for the row that it's in. But it does not provide any context. As I said, they settled on a single null. It doesn't tell you why it's missing. It just says it's missing. It's unknown. It doesn't equal anything, including itself. So one doesn't equal null, obviously, but null also doesn't equal null because two nulls are two unknowns. Does one unknown thing equal another unknown thing? That's unknown. We don't know. And it's not any particular data type. So when you're working with it, it's not converting things to null or out of null. If you do a select into in SQL, into a new table and you have a literal null in your select statement, you'll get an integer. And that's not because it has anything to do with integers. It's just because that's like the default type for SQL Server. So if you have this unknown thing and it doesn't equal anything else, how do you compare it and test for it? Those of you who've had some formal programming training or have taken logic and philosophy or worked with circuits will be familiar with a truth table. This is a truth table that incorporates null as a third option. So on the left here, we have all the potential values for x or y, so true and false, and then all the combinations of those two values. And on the right side, we have the result of applying different operations to them. And what you'll see is that with null kind of takes over a whole huge section of this table, because when you compare anything to null, it is always null. Nothing doesn't equal null, which is a kind of a tough concept for people sometimes. If x is true and y is true, then it's true. But if anything is null on either side, the result is also null. And for or, you will get a null unless one of those two values is true. So if one is false and the other is unknown, that unknown, is it true? Is it not? It's unknown. So that's the result you get. So including null as another option ends up just kind of you get a lot more nulls as you start to work with it. So how can we work with it? And the best way to do that is with some demos. So let's show how we work with null. And before I get into the demos, I'll ask you, Raitza, at this point, are there any questions?
No questions so far. You're good.
Okay. There's always 7 minutes in, but figured I'd ask. Okay, so first thing we're going to do is set up some tables to work with. And these are really tiny tables because they're for demo purposes. I've got in each one an identity, an automatic numbering of 1 through 8, and a value that is an integer. In the first one, I've got the Fibonacci sequence 1, 2, 3, 5, 8. And the second one, I just have odd numbers 1, 3, 5, and 7. So this will give us some things to work with because there's some of the same values in both tables. There's some different values in each table, and there's some nulls to work with. And before I move forward, I do want to address a question that I sort of brought up before, which is what is null really? And I said it's a marker on a field. What does that even mean when you are talking about SQL Server? If we look at the table definition, we can see here, yes, this column is nullable. So what does it mean when we put nulls into the table? I'm going to use a couple of undocumented but well written about dbcc commands to look at what SQL Server is actually putting in here. And the first one is this dbcc end. This tells us where our data is in terms of indexes, our index pages. And every table has at least two. There's what's called an index allocation map, which is this page type 10, and the actual data when data pages are type 1. I'm going to go grab that number, which actually is already in here because this changes sometimes. And then we're going to use dbcc page, and this is going to tell SQL Server, go look in this page and tell me what's actually there. So this is how the data is stored in SQL Server. And if we go down here, so this is the entire table because the table is so small, it fits in a single page. SQL Server stores all of its data in 8 kilobyte pages. And if we scroll down here to where it says slot 0, these are actual data rows. Everything else is, most of this, rest of this is header sort of metadata stuff. But here's our actual data, and we can see that it's a primary record, and it has an attribute of a null bitmap, and this entire record is 12 bytes long. It's our record size 12. And here we can see our data. We have record ID and value, and they're both 1 for this row. If I scroll down a bit to row 4, here's our null. So what is the null? The null is actually this, the null bitmap. In every record, in every table, there is a null bitmap, except for extremely rare circumstances. Every table has a null bitmap on every row, and the null bitmap is a set of bytes, and each bit in the byte corresponds to a single column in the table. If the number of columns is not evenly divisible by 8, then you'll have some extra bits, and SQL Server keeps track of which bits actually correspond to a column and which ones don't. And so what the null is, the marker on the field, is this null bitmap for the second column in this row. That bit is set to 1, and that is what null is. And SQL Server can leverage this. If you say select count star from the table where this value is null or is not null, then it will look in the null bitmap. It won't actually go look at the columns to see do they have data in them. It's going to go read from the null bitmap and tell you, return back a number based off of how many of those bits are set. So that's what a null really is in SQL Server. And I do want to just real quick show you that if I create a table that has 2 non-nullable columns, and we look at the data page for that, as I said, this changes around sometimes, and we go down to our data, we still have a null bitmap. Like I said, every table has them, except in extremely rare edge cases. SQL Server will, on other kinds of indexes, like just standard index, non-clustered indexes, if all of the columns are not nullable, then it will not include a null bitmap. It knows that it doesn't need it, and so it'll leave it off for storage purposes. And the last thing I'm going to do here is create a numbers table with 100,000 numbers in it, and then we're going to use that in a later demo. All right, so we know what null is. Let's go see. Start off simple with looking at our tables. So we have those 2 tables. Well, actually, this one's only going to use the first one, which has the Fibonacci numbers in it with 8 rows. And if I run this, I'm going to get, so let's see. So if we say, show us all the ones where the value does not equal null, like I said, nothing doesn't equal null. So we get back nothing. Instead, if we say where the value is not null, then we get back all the records that have a number in them. And this is one of the things, when people are first coming to SQL that seems a little weird, is that for this one particular attribute value, you need a special operator. Equals and doesn't equal works for everything else, but for null, you need to use is or is not. And you have to know that there's these special operators that deal with them. Same thing as holds true if we say value equals null, we get back nothing. And if we say where it is null, then we get back our 3 records that have null in. Okay, so we know we can't use the standard operators with null. We have to use is or is not. But what about if we want to compare the 2 tables? So as I said, I've got Fibonacci sequence and odd numbers. So if I'm going to select everything from table A that has a value that is also in table B, I'm going to get back, I should get back 1, 3, and 5, because those are the odd numbers that match up with table B. And if I run this, that's what I get. I get 1, 3, and 5. And that's because this is the same. If I run this select value from table B, that's the same as saying this 1, 3, 5, 7, and null. And because in essentially is a big or statement, is the equivalent of this statement, which also will give us back 1, 3, and 5, because 7's not in the table, and all of the equal nulls these return null, right? And if you OR with a null, only the true values are returned. So 1, 3, 5 will come back. And if we look at the actual, if we run this with the execution plans, so for this first one, where I've said where its value is in 1, 3, 5, 7, and null, I know this is tiny, but I'm going to zoom in here. We can see that this is what SQL Server is actually interpreting that as. It is literally converting in 1, 3, 5, 7 null to 1 or 3 or 5 or 7 or null. No, it gets rid of the null. It knows that null can't do anything in this instance, and so the SQL engine gets rid of that as the part of parsing and optimizing the query. And in fact, it does the same thing for my other statement where I explicitly said a whole bunch of or nulls. It just drops it out, says no, I'm not even going to bother. 1, 3, 5, 7 are the only values that could possibly work in here. So SQL is optimizing out nulls where it knows that it can't use them. Another way that we could look at this, so I think most SQL developers are familiar with union. Gives you all the values from 2 different sets and gives you the distinct values from the two of them. So if I do a union, I get back 1, 2, 3, 5, 7, and 8, along with the null, because it does exist in both tables. And this is the first place where we see things being a little bit inconsistent in the implementation, which is that in this case, if we're saying we want to see all the distinct values, null counts as a value. And so if we're comparing table A and B and they both have null, we're going to get back a null, because in that case, you can consider it to be treating nulls as equivalent, even though if we say where null equals null, that's going to come back with nothing. So the other one we can use in terms of the equivalent of giving returning everything from A that is also in B is intersect. And intersect does that. So if we say select everything from A, intersect values from B, again, we'll get back 1, 3, 5, and the null, because the null exists in both tables. If there was no null in B, we would not get back a null from the intersect. So it is treating the nulls as equivalent for these set operators. Okay, so what about the opposite? If we say, I want to see everything from A that's not in B, and we know that B has all odd numbers in it, so I would expect to get back 2 and 8, because those are the only even numbers in table A. They're not in B, and so that's what I would expect to receive or return. So if I say select everything from table A, value not in all the values from table B, I get back nothing. And this is where people who are newer to SQL, and sometimes this can even catch more advanced developers off guard, is when you know that there's values in your initial data set, and you're saying, give me everything that's not in this other one, and you get back nothing. It almost feels like a bug or an error, but it's not. And it's because of the way that the logic works out. And that logic gets a little complicated, and it's more complicated because null is involved. So as we said, in is the equivalent of a big OR statement. So this not in like value, this is the equivalent of where everything from table A, where not, values are 1 or null or 3 or 5 or 7. And not a series of ORs is kind of a weird thing to work with. We can simplify this in classic logic. You can distribute a negation, that's what our not is. We can distribute the negation across the ORs, and you do that by sort of reversing everything. So not a series of ORs is the equivalent of this statement. Value, where give me everything from A, where the value does not equal 1, n does not equal null, does not equal 3, etc., etc. And the problem is that nothing doesn't equal null. So this statement, value does not equal null, will return null. And when you end null with anything, you get back a null. And so this, any null in table B, you only have to have one. You could have this, could be a million row table. One null in here is going to essentially serve as like a poison pill and wipe out any results that you might get, because the not saying where that value does not equal null returns a null and ruins the whole thing. So these two statements also will return nothing. So the way what we really wanted here, right, was this. Everything where the value is not equal 1, 3, 5, or 7, and leave out the nulls. And if we do that, we do get back 2 and 8. And so the way we would write that typically is to add a predicate, add a where clause to our subselect, and eliminate the nulls before we do the not in. And if you forget to do this, you're going to potentially get yourself in trouble. So if we do this, we say select everything from table A, where the value is not in all the values from B, where those values are not null. Now we get back 2 and 8, which is what we expected in the first place. So eliminating nulls while you're doing logic is something that you really have to think about when you're building out your queries. Another way we could have done this is with the except statement. And except is the opposite of intersect. It's not nearly as well known, I think, as union. But it does make things, it can make a lot of statements much simpler. And it works, like I said, like intersect, but in reverse. So it says everything from A except what's in B. And so it's going to compare all the values, including null, and only return ones that don't match. The even bigger advantage of except is that, I'm doing it here with one column because I only really have one. You can do this with as many columns as you want. It's a select statement. And so if you have two tables, it's great for QC. I use it all the time. If you're comparing two tables, say you're doing some manipulation and you've got two sets and you need to make sure that they are equivalent, you can select everything, all the columns that you need from the first table, except all the values from the second one. And then if you really need to make sure they match both ways, you can then flip that around and have another SQL statement that says select all the columns from B except what's in A. And if you do that and they both return nothing, then those two data sets are identical. And it's an extremely efficient operation. So you can very quickly compare two tables and make sure that they're the same. And as I said, it's going to treat nulls the same. So you don't have to do any substitutions or special handling for those nulls, except is going to treat them as equivalent and make your queries much simpler to read. So I mentioned substitutions, and that's what isNull and coalesce are for. So isNull and coalesce, they feel sort of interchangeable sometimes. They're very similar, but their design in the back end is very different. And for a long time, I kind of felt that isNull was maybe just a wrapper around coalesce for two attributes, but it's not. It's designed completely differently. Coalesce is the SQL standard, and as such, has a fairly long definition in the ISO standard. And it's designed to return the first not null value from a list of values. isNull, on the other hand, is a Microsoft T-SQL extension. It is custom to SQL Server, and it takes two values. That's it. Whatever it is you want to potentially replace, and the replacement value, and that's it. So it's a very simple implementation. Let's look at some differences between the two. Well, first, if we just use them as, we're going to substitute one value for null, they do work basically the same. In this case, anywhere there's a null, instead I'm going to get a 0, which is what we would expect. As I mentioned, coalesce can take multiple values. So if we join the two tables together and we want to substitute the value from B where A is null, then we're going to get things like this, where A is 2 and B is null, we'll get 2 for isNull. And where A is null and B is populated, we're going to get back the value from B, which is what we wanted. But where they're both null, we're still going to get null, because this only takes two values. Coalesce, on the other hand, I can add as many as I want. It's a whole series of potential values. And the first one that is not null is the one that's going to be returned. So if I provide a literal value as the last one, now I know I'm always going to get back something. I could put another isNull around this isNull and have the third substitution. But as you start nesting functions, it starts to get harder and harder to read. But as I said, they do function a little bit differently. And the difference is mainly in the data types returned. isNull will always return the data type, the value it returns will always be in the same data type as the first argument. With coalesce, the standard says it will return the data type of highest precedence from all the options provided. So this can cause issues when you do things like a select into. So if I create a table and I select into A, and I'm going to have a bunch of substitutions here. We do a select from it. You can see mostly it looks the same, although we already start to see something interesting here with our numeric. And if we look at the table definition, we're going to see, so value itself is a tiny int. All of the isNulls are also tiny int. As I said, it's always going to be the data type of the first argument. However, the coalesce goes by precedence order, and there is an entire list in the Microsoft documentation for type precedence, if you need to know it. And we get things like this. So if we coalesce with a string as our default, well, we'll still get back a tiny int because any integer has a higher precedence than any string, varchar and varchar data type. But numeric has a higher precedence than integers, and float also has higher precedence than integers. So I started out with a 1-byte data type, and when I coalesced to a numeric, now I'm going to get back a 5-byte data type, and with float, it's even an 8-byte data type. So what this means is, one, select into. If you're not careful with casting things, you can get back columns with data types that you weren't intending to. But it also means that if you're using coalesce in where clauses or in join clauses, you can be introducing potentially implicit type conversions that you don't mean to be, and that can cause performance issues. So you need to be careful with either casting your substitutions to the correct type or casting the result of the coalesce to the proper data type when you're using it, because you might be getting back data types that you don't anticipate. I'll pause there for a moment. Right, so are there any questions?
No questions at all. I think everybody's riveted like I am.
All right, excellent. Okay, so let's talk about summing things up, aggregation. For this one, I'm going to put together a couple of different demo tables. So I have one that's a standard 8-row table and another that is pivoted out. So in the first one, I've got the values 50, 50, 100, and 0 with nulls in between. And for the other one, I have a single row with 4 columns. One of those contains a null value, but otherwise it's the same 50, 100, and 0. So if we count all the records in our first table, ag demo, we'll get back 8. Count star will always give you back the number of rows in your table. It doesn't actually look at the data, it just says how many records are there. There's 8. But if I count on a column, I'm only going to get back 4 because there's only 4 populated values, and it eliminates the nulls. And in fact, there is, by the SQL standard, it has to give you a warning that it is doing that. And I think a lot of developers are familiar with this statement here: warning, null value is eliminated by an aggregate or other set operation. That's SQL Server's version of the warning. The SQL standard says it has to issue a warning, and that's what it's doing. Is it's eliminating the nulls and then counting the values. If I count the distinct values, it's going to get rid of the duplicate 5s, and we're going to say it's going to tell us that we have 3 distinct values, again eliminating the nulls. But if I say give me the distinct values, I'll get back 4 records. And that's because null counts as a distinct value, even though it's not really a value. So we get back 4 records: null, 0, 50, and 100. And that means that if we're using that in a subselect and then counting, we're going to get back 4, which means that we get back a different number if we get select count star from select distinct, or if we count distinct. And so it's something to just be aware of. Could potentially, throw off some numbers in your queries. And again, these are simple demos, but you can consider this select distinct could be coming from a view, and then your count star is happening in another query that's querying that view. And so you just need to be careful about how your data is flowing. So if we sum things up, if we group by value, well, null is going to be one of those groups. So null gets eliminated from the aggregate operations like count, but when you group up, it does get counted as one of the groups. And so if you are doing reporting and you're grouping on something that can contain nulls, the null group, which all the nulls will roll up to, even though null doesn't equal null, in this case, it's treated all as kind of one thing, that null group can quickly swamp the results from the rest of your report. And so you either need to treat it like a value and give it a substitution with an is null or a coalesce, or you want to eliminate it, in which case I could add a where clause here, select count from ag demo where value is not null, and eliminate it from my result set. I want to point out that we know that ANDing and equaling things with null yields null. So does adding things to null. So the single null value that's in second value here, if we add these columns together, that will return a null. But if we sum up from our ag demo table, again, nulls are eliminated in aggregate functions. And so even though there's nulls in these rows, they don't ruin the sum, and we get back 200 because adding up the 50, 50, 100, and 0. If we take an average, again, it's eliminating the nulls first. It's getting the 4 values that exist or that are populated and dividing by 4. But what if we need those to count? If those null values, those null rows, are actually, maybe they're incomplete records, but they need to count towards your total, your average. Well, then you need to substitute something in its place. And so that's where if I coalesce the value to 0 within the average, now they're not null. They're not going to get eliminated. And so I'm going to total up and still get 200, but now I'm going to divide it by the 8 records that are in the table for an average of 25. So nulls will be eliminated from averages if you need them to be there so that you're not over-reporting. Then you need to do a substitution. Min and max also eliminate nulls, and we get our warning here that they're being eliminated. So min is 0, max is 100. Least and greatest were added in recent version of SQL Server, which I'm very happy about, because sometimes we need to do this across columns instead of rows. And they will also eliminate nulls. So least is 0 and greatest is 100, but you don't get a warning, which I kind of find interesting. Okay, so we've talked about comparing the null, we've aggregated null. How much space are we using to store null? How much space does a null take up? And this is, this was something I wasn't all that familiar with, and I found this really interesting. So we're going to start off with a demo table that's got 6 nullable integer columns. And I'm going to fill that with 100,000 rows. That's what that numbers table I set up in the beginning was for. And we can see I've got a table full of nulls. It is empty, except it's got 100,000 records. And our, auto number here, record ID. So how much space does a table full of nothing take up? And the answer is about 4 megabytes, or 481 reserved pages. Like I said, SQL Server stores everything in 8 kilobyte pages. 481 times 8 is going to equal 3848. So these do correlate. But sometimes, it's easier to talk about megabytes than pages. So, okay, we have 4 megabytes of nothing. What if I fill in one of those columns? If I set column D to an integer value, if I do that, I'm still at 481 pages, 4 megabytes. And in fact, I can fill in the entire table, and it will not take up any more space. And this is because of the way that SQL Server stores the data on disk in pages. It uses something called the fixed var format. So you have all the fixed length data is the first part of the format, which is in the green here. And all the variable length stuff is at the end in blue. And in the fixed side, we have things like metadata and bytes that tell SQL Server how long the fixed length data section is, where it ends. What is the actual fixed length data. A couple of bytes that tell SQL Server how many of the bits in the bitmap count for the null bitmap. Like I said, if you have a number of columns that does not evenly divide by 8, there are going to be unused bits in the bitmap. So the null bitmap column count tells SQL Server how many of those bits matter. And then you have the null bitmap itself. And these are always the same size for every row, as long, while that table exists. If you alter the table, or if you alter column sizes, things, it will change this. But from that point on, it's always the same size. And then you have the variable length data. This table has no variable length data. It has 7 integers, six data columns, and then my identity column. And all of those, integer is a fixed size data type. So all of the data is being reserved. Essentially, SQL Server is reserving the space, the 4 bytes for each of those integers in the fixed length data section of the fixed var record. And so when I populate a value, when I set column D to 100, it's not taking up any more room. That space already, those 4 bytes are already allocated. They're already in the row. They're set to something. We don't know what when it's null. And the null bitmap has a bit set to 1. And so what happens when I populate the value, and I set that column D to 100, it sets the data to 100, the binary version of that, and then flips the bit in the bitmap from 1 to 0. And at that point, it says that column's populated. If you query it, it will get back a value. When that bit is set to 1, it says null. I'm never going to give you back anything. So that's why populating the data in here doesn't change the size of the table. Everything is fixed size. Okay. So what about variable length? That's where things get interesting. The size of the data, the size of the table, is going to depend on the data types involved and the types of data types, and then the position of the data in the row. And we usually say with SQL that column order doesn't matter. And for logical purposes and query purposes, that is absolutely true. But for storage purposes, it very much does matter. And I'm going to demonstrate that. So we're going to recreate our table with 13 variable length, so varchar 10 columns. And again, it's full of nulls. There's double the number of columns now. How much space does that take up? The answer is a little less than half. It's only 1.5 megabytes now and 193 pages. We were at 481 before. Now we're down to 193. So we've got more columns. We're taking up less space. Okay, what's going on there? If we look at our table, now we have a whole lot of pages because we've got 100,000 records. We're going to pick one of our first data pages, which actually happens to be the same number as the last time I ran this. And we go down here to where our data is. So where it starts to say slot 0. We can see its primary record, null bitmap. It is 12 bytes long. And here we can see the record. It's got, let's go a little too far. So we can see, here's record 2. Record ID 2, all these columns are null, and they're all 12 bytes. So what's happened is with the fixed var format, SQL Server at this point doesn't need to track anything about all of these empty columns. It knows that they exist. It's in the header information, but there's nothing in the data. So what happens if I populate the first column and I say set column A to the letter A? This is a variable, it's a varchar. Each character is 1 byte. So now we've added 1 byte to every row. We've added 100,000 bytes essentially to the table. How much space does that take? Well, now we're up to 2.8 megabytes and 353 pages. And if we go look at our page, we can see now that here's our number 1, our letter A, everything else is still null. And our record size, 2 things have changed. 2 other things have changed. In our record attributes, we now have an attribute called variable columns. And our record size is now 17 bytes. We were at 12 bytes before. We've added 1 byte, the letter A, but we've gone up by 5 bytes. So why is that? Why are we now taking up 5 bytes to store 1 byte of data? And that's because of these other pieces here. So what we've added is that in the variable length, so SQL Server now has to track the variable length data. We've populated something in variable length data. It's had to add this entire section to the row. And so the first thing we have is 2 bytes that track the length of it's how many variable length columns there are on the row. So it's 2 bytes that contain essentially a number for SQL Server to track how many variable length columns there are of all kinds. It then has an offset of 2 bytes per column to indicate where the end of the last populated value is, and that's going to be the key. And then we have our actual data. So at this point, we've added 2 bytes for the column count, 2 bytes for the offset array, and 1 byte of actual data. And that's where our 5 bytes comes from when we've only added 1 byte of information. Okay, well, what if we populate something in the middle? So if we empty out our entire table and recreate it, and then we set column F, well, now we're up to 5.5 megabytes and 697 pages. We were at 353 before. Now we're at 697. And if we go look at the page now, same thing. We have number 1, we have the letter F, everything else is empty. We've only still got 1 byte of information. But now our record size is 27 bytes. And if we were to do the last column, column M, and we look at that, now we're up to 8 megabytes and we're over 1,000 reserved pages. And every row is now 41 bytes. You can see here letter M, the letter M is populated. So we're up to 41 bytes per row. We're still only tracking, we've still only added 1 byte of actual information. All the rest of it's overhead. So here's an analysis of what we've done. So this is what's in storage right now. Every record has 2 bytes for the record status, 2 bytes tracking the length of the fixed length data, 4 bytes for our fixed length data. That's the record ID, is a 4-byte integer. 2 bytes for our column, our bitmap column count, because we have 13 columns. So it's over 8, needs a 2nd byte to track the additional columns. Our bitmap itself is 2 bytes. That's like I said, we need 13 of those bits to track all the columns. When we first started out with nothing populated, it didn't track any of the variable length information. So there were 0 bytes at this end of the row. When we populated just column A, now we've got to track the end of it, and that's 2 bytes. We added F, now we have to track A through F and where each of those columns ends. And so we've added 12 bytes per row and then 26 bytes if we populated just the last column. So the further down the row your last populated variable length value is, the bigger the row is in terms of storage. When we talk, maybe you've heard that variable length columns take an extra 2 bytes. These are those 2 bytes that they're referring to, is the offset. This is a more simplified version. I've condensed the fixed portion down to a single value, because it's always the same, 12 bytes. And here's our offsets increasing, and we can see how many bytes per row that corresponds to, and the total number of bytes of storage required to track all of that. And as you can see, if you have a lot of empty columns, your offsets can quickly become a large portion of the data that's being stored on disk to track where those columns are. As a more visual representation of what we're doing, and this is why the rows get longer and longer, is when we have no data, we don't store anything. As soon as let's populate column A, we have to track the column count, the offset, and the data itself. With F, we have to track everything in between, the end of every column. And then with M, we have all of it. This can feel sort of like I've gone really down the rabbit hole, but it does have a practical application. Most of us, I think, work in systems where a lot of us work in systems where we're ingesting data from other systems, and especially data warehousing, which is where I am. We're constantly reading in things from other systems. And typically the data that we're getting, people tend to design tables and outputs, exports, with all the important information at the beginning and less important information at the end. It's kind of human nature. And so a lot of times the ends of the rows of data that we're pulling in are going to be a lot of nulls, depending on the system that it's coming from. And then what do? We read that into a table, and we track things like the create date and the create user and the name of the file that it came from. And most of those are variable length values. And we put those at the end of the row. So we're always populating the last variable length value, which means that any nulls between the last populated one and the end of the row has to have offsets to be tracking that information. We're storing a lot of overhead to keep track of nulls. And so one thing we might consider doing is moving our metadata to the beginning of the row so that any nulls at the end don't take extra space. What are some other things that we could do to not worry about that? One is something that was introduced back in 2008, SQL Server 2008, which was sparse columns. And I will lead this off with a big caveat that sparse columns have a ton of special conditions, and you really need to know what you're doing with them. But they were designed around this. The idea behind a sparse column is that you assume it will usually be null. And so if I recreate my table, exactly the same, but now all these are sparse, and I look at that table, it takes up actually a little bit less. Every one of these rows is 11 bytes instead of 12. And it stores, so I've got 1.4 megabytes and 177 pages. If I populate column F in the middle, we're at 4 megabytes and 489 pages, which is a little less than it was when we populated column F before. And the table structure is kind of interesting. So we look at page 808. Oh, that's what I had last time. Oops. Here we see, as you remember, before we could see all of the nulls, so this record is now 24 bytes. But we only see our record ID and our populated value. All those other columns, all those other nulls, they're not here. They are not represented in the data. They take 0 bytes. They're basically not there. And that's the intent of sparse columns, is when your values are null, they take no space to store. When you do populate them, however, you're going to pay a penalty. It's instead of 2 bytes of overhead, it's going to be 4 bytes for every populated value. And so there is a big chart on the Microsoft documentation for what percentage of your column has to be null based on the data type in order to see any space savings. And so you really only want to do this with columns that are almost completely empty, and that will continue to be completely empty. If it's a column that some application developer might decide to start using and start populating, if that happens and you're not paying attention, you could very quickly have your storage explode, because you are now paying this overhead to populate all these values that you've basically told SQL Server, oh, don't worry about it, that will almost never happen. Now it's being populated all the time, you're going to pay for the storage. So you really need to know your data extremely well to use sparse columns. There's also a bunch of places, there's a bunch of attributes that they can't have, but they can save space. The other way to go, and probably the better thing to look at, would be compression. Page compression, row compression are going to eliminate nulls essentially when they compress the table. So you might pay the offset price and stuff in memory, but you're not going to pay it on disk. So once they're decompressed, then they still have the same structure, but on disk they will take up much less space, because all of that overhead or the offsets and stuff, that all gets compressed out. So compression is probably the better way to go, but sparse columns are there if you have a column that this is almost never going to get populated, or only one row in an entire table is populated. Sparse might be something to look at. Okay, I'm going to pause there before I move on. All right, so any questions?
Still no questions, and you have 10 minutes to go.
Excellent. Okay, so when you're working with null, how do you keep from being surprised? As we saw, sometimes when you're querying and you do things like a not in, or things like that, you could get surprising results, and we never want to be surprised with our code. Consistent, reliable code is the best code, and so we don't want to be surprised. So what can we do? Well, the first thing we can do is tell SQL Server more about the data and apply constraints. If a column should not contain nulls, make sure that you're applying a not null constraint. Nulls have a tendency to sneak into your data, even where you don't expect them to show up. So setting not null is first way to make sure that you're never going to have that happen. And setting defaults. If you're using not null, a lot of times you'll use a default. Even if it's nullable, you can set a default, and then only explicitly null values that are designed to be null will be populated with null, because you'd have to explicitly set that. Check constraints, and I'll talk about the difference between check constraints and with check option, because they both have check in the name, but they actually operate very differently. So a check constraint on a column lets you say something like values for this column must be less than or equal to 10. But if you insert null, that will work. Even though null is not less than or equal to 10, check constraints don't check against nulls. If you want that column to not be null, you need to also set a not null constraint on it. With check option, on the other hand, is an option that you apply to a view. So when you're defining your view, you could say return all the things from this table where value is less than or equal to 10. And if you say with check option, when you go to insert into that view, and insert updatable views are great for maintaining data integrity. If you go to insert into the view and that value is null, you will get an error. SQL Server will not let you insert the row, because it will only allow you to insert records into the view that would be returned by the view. And since null is not less than or equal to 10, it would never be returned under those conditions. And so SQL Server will prevent you from inserting that value. So with check option, will prevent insertion of nulls. Check options, check constraints will not prevent insertion of nulls. Something else we could do is normalize. If you have columns that are mostly empty for certain types of rows in your tables, that can indicate that you're storing different kinds of entities in a table. And that is an opportunity for normalizing. You can break those entities out into new tables, and the columns that were always null for that kind of record, you don't include them on the new table. And the columns where in the rows, the types of rows where they do apply, then you do include the column. So that's, when we talked about missing but applicable, missing but not applicable, if they're usually null on a row because it's not applicable to that kind of row, that's something that you could normalize out. And then you don't have to worry about handling the nulls for columns for the rows where those values don't apply. That's more for transactional databases. In warehousing, we want to instead, we're using these star schemas, facts and dimensions. You want to make sure that for any column on a fact table that is a dimensional key, there's an entry in the dimension that represents unknown or missing information, and use that key in your fact table rather than simply having a null key value. That's extremely important for working with BI tools, Power BI, Tableau, all these. If you have null dimension values and you are doing any kind of reporting where you're joining your dimensions and then filtering, any row that doesn't have a key is simply going to drop out of your results. Same thing goes with metrics. If you are grouping up by metrics, summing up by metrics, and there are nulls, those records will simply not appear in your result set. They'll just drop out. And so you could be potentially underreporting or misreporting data unintentionally, and that can lead to a lot of problems when you find out that your report is actually missing a whole bunch of information because the key value that you're using is null on those rows. And I will kind of have a shout out here to 6 normal form. 6 normal form is a normal form that does not include nulls. It tries to implement, I mentioned CJ Date and others, advocated for not having any nulls in the relational model. It's kind of working towards that. And so what it means is that any row where you have a null, it means that you have to break that out into a different table. You end up with a huge number of tables and a huge number of joins. Six-normal form is typically not practical, but it does exist. And if you want to learn more about normal forms, I would highly recommend Hugo Cornelius's discussion on normal forms. Okay, so hopefully you've learned today that about why null is such a difficult topic, that it's been discussed for the last 50 years, that the relational data model has been around and continues to be debated. It affects all aspects of development, from architecture down to application logic, and needs to be considered at all of those levels, including at the storage level. And that understanding how null behaves and how to treat null and where you need to be careful with it can help you produce better code. Thank you for joining me.